Swayam Prabha. Digital India. Educated India.
Okay, so last time we started with the concept of statistical ensembles. And so far we have discussed two ensembles. So, one being microcanonical and the other being canonical, right. And the way we understand microcanonical ensemble is that we have a system. So, we have these various copies of microstates, mental copies of microstates with fixed energy, right. So, we keep the energy fixed. So, this system has some fixed number of energy, fixed number of particles, and its volume remains fixed, right. The way we basically conceptualize this was, so we divided this system into two subsystems. So, we call this subsystem 1 with energy E1 and number of microstates in this subsystem 1 as omega 1, which is a function of E1. Similarly, subsystem 2 with energy E2 and number of microstates, which is which is omega 2, which is a function of E2, right. And basically what we did is we basically defined the condition for thermodynamic equilibrium to be the state where the product of these two microstate achieves a maximum value, right. So, we said that that is where the system wants to be, and that is the equilibrium state. And we saw that when we use this concept, and when we use the concept that the entropy indeed can be written as Kb times log of omega, where omega is the number of those microstates, the results that we obtain from this this statistical ensemble and thermodynamics, they match with each other, right. So, they are in so they are exactly matching with each other. So, there is no difference so the results match with. So, when we use the concept, that the entropy can be written as Kb times log of omega, the results that we obtained from statistical ensembles and thermodynamics were in accordance with each other, all right. And we also saw that if we have if we divide this system into two subsystems such that E1 and E2 are almost equal to each other, right. Like they are not much greater or smaller than the difference between those two is not huge. So, we saw that the subsystem 1 quickly achieves a value, an average energy value, which is given by P of E1 bar, right. So, so basically this is the average energy of subsystem 1, right. So, average energy, right. And we also saw that the fluctuations around this average value were very rare, and in fact we looked at the distribution of this energy around E1 bar, and we find that P of E1, the distribution of this energy, is given by E1 bar exponential of minus k times E minus E1 bar whole squared, right. So, the fluctuations around this average energy, they fall exponentially quickly, right. So, therefore, the subsystem 1 quickly achieves an average energy E1 bar with fluctuations being very rare. On the other hand, we went to the other extreme of microcanonical ensemble, where we now assume that the subsystem 1 rather than being almost equal to subsystem 2 is much smaller, which has an energy epsilon, and the associated number of microstates is omega epsilon, right. And therefore, the energy of, now we can call this subsystem 2 as reservoir, is E minus epsilon, and number of microstates is omega, we can just call it omega, which is E minus epsilon, right. And remember, this is still a microcanonical ensemble in a way that our system plus our small system plus the reservoir is still insulated, right. So, the number of, so E and V is still fixed for this entire system. However, so E and V are still fixed for the entire system, all right. But the important point here is that the epsilon now is much smaller than E minus epsilon, right. And we saw that now the energy fluctuations in this small system, right. So, if epsilon is much smaller than rest of the energy, so the distribution of energies basically goes exponential. So, minus beta epsilon, where beta was 1 by kBt, right. And in this case, we can call our subsystem, the small subsystem, as the canonical ensemble, right, because the energy fluctuations are huge. The energy of this system is not fixed. However, the temperature of this system is fixed, which is decided by the external system, which is E minus epsilon, the other subsystem, which I am calling reservoir, and this temperature dictates the energy state of our system, right. So, the canonical ensemble is typically an ensemble which has fixed temperature, but not energy, all right. Energy can fluctuate hugely, right. And we also saw that at any given moment, the probability to find this subsystem in any energy state P of epsilon I is given by minus beta times epsilon I divided by sum of probabilities of all states e raised by minus beta epsilon j, and in this case the denominator, so this quantity is also known as canonical. So, this is canonical partition function. So, this is what we did in the last class, all right. So, today basically we will use this canonical partition function to derive various useful quantities in a canonical ensemble, all right. So, let us do that. So, basically the first thing that we will do is we will try to calculate the average energy in canonical ensemble. In a canonical ensemble. Okay. So, maybe I'll repeat myself. So, remember, in microcanonical ensemble we said that the subsystem 1 achieves an average energy E1 bar and the fluctuations around that energy are tiny, all right. However, for a canonical ensemble the energy can fluctuate a lot, right. So, in fact, there is no one fixed energy that we can associate this system with, but still we can calculate the average energy of this system at any given point, all right, and that is exactly what we are going to do, all right. And from now on I will drop the sign epsilon and I will just use energy symbol E, all right. But you should understand that now a canonical ensemble that we are discussing, right, with energy E, it is in contact with some huge reservoir much bigger than our system, which has a fixed temperature T, right, and energy exchange between our canonical system and the reservoir does not really change the temperature of the reservoir, all right. So, that underlying assumption is always there, okay, all right. So, clearly by definition we can define the average energy of any system basically can be written as sum over j E j times probability of having that energy, right. So, energy times probability, and I can rewrite this as follows. So, this is just j times this summation over j E j, and I can now substitute P E j which is nothing but minus beta times E j divided by the canonical partition function, right. and we can see, which I will just now show in a minute, this can be written as minus del by del beta of log z, and this can also be written as minus 1 by z del z by del beta. Okay. So, let us see how, right. So, basically how. So, we can see a negative of partial derivative of log of z with beta basically just becomes minus 1 by z, exactly this thing, log so del z by del beta, right, and this I can write it as follows, minus 1 by z del by del beta, and I am just substituting for the value of z, right, that by definition z is sum over j e raised to the power minus beta e j, right, and you can see that this is exactly okay. So, you can see that this is, if I take the derivative, so this just becomes sigma j 1 by z. So, minus e j, so e j will become minus e j will come in the come down and it will cancel with minus sign. So, I will left with e j e raised to the power minus beta e j, and you can see that this quantity and this quantity are same, right. This is e j times e raised to the power minus beta e j divided by z, right. So, therefore, the average energy can be written as negative of the partial derivative of log of partition function with respect to beta, where remember beta is inverse k b t. Okay. So, maybe I can write here. So, beta is 1 divided by k b t. Okay. All right. But also we must remember that this average energy is averaged over all the copies, right, all the mental copies that we are considering in an ensemble, right. And from ergodic theory, ergodic principle, we know that, okay. So, basically what I am saying is this average energy is equivalent to the internal energy of a system in thermodynamics, right. So, where U is the internal energy in thermodynamics. Okay. And the system that we are considering in thermodynamics is again a one which is in contact with a huge reservoir, right. Say I give you a collection of gas with conducting walls and I put it in contact with certain constant temperature, or I will keep it in atmosphere which is at certain fixed temperature, right. So, then this U will be the internal energy of that system, all right, and that is why it is a canonical ensemble. Okay. So, the second thing that we can calculate is the variance of energy. Okay. And by definition, the variance of any quantity is given by the average of E minus average E squared and this average, right. So, basically so the difference of energy values with its average and square of that and average of that quantity, all right. And this we can very easily expand and write it as follows. So, this becomes E squared plus average E squared minus 2 times E times average E, and average of this thing, right. And I can now rewrite it as follows. So, this is E squared average plus average E squared, average E squared minus 2 times E average squared, right. And this can simply be written as E squared average minus E average squared, all right. So, we already know what is E average. So, E average is given by minus del by del beta of log z. So, okay. So, for this we basically now have to calculate what is average of E squared, all right. So, by definition, right. So, by definition, E squared, so E squared average is basically just equal to sigma j E j squared times P of E j, right. So, this is just by definition, and this can be written as j sum over j ej squared e raised to the power minus beta ej divided by z, right. So, that is by definition, and we will now prove that this can be written as 1 by z of second derivative of partition function with respect to beta. Okay. So, let us see how, right. So, basically, so let us prove. So, I can very easily write 1 by z del square z by del beta squared equals so 1 by z del by del beta of del by del beta, and let us replace z which is sigma j e raised to the power minus beta e j, all right. And I will take its first derivative. So, this becomes del by del beta of sigma j, and minus e j will come in front. So, minus e j times e raised to the power minus beta e j, right. And if I take another derivative, so this becomes 1 by z. So, there will be minus and for simplification I can just write sigma in front, right. So, this becomes 1 by z e j squared e raised to the power minus beta e j, right. And you can clearly see that both these quantities are same, right. So, this is exactly same. So, therefore, my E squared average can be written as 1 by z del square z by del beta squared. Okay. So, but also earlier we saw that average energy is given by 1 by z minus 1 by z del z by del beta, right. So, and also from previous result we know that average E squared is 1 by z square del z by del beta squared. So, therefore, finally, the variance which is E squared average minus average E squared. Okay. So, therefore, the variance in E is basically this minus this, right. So, this is 1 by z del square z by del beta squared minus 1 by z square del z by del beta squared. Okay. And again we will see that this can simply be written as follows. So, this is second derivative of log z with respect to beta, okay. And let us prove that. Okay. So, how is that? Okay. So, second derivative of log z, so I can just split it into 2. So, this is del by del beta of del by del beta log z, right, and this simply becomes 1 del by del beta of 1 by z and del z by del beta. Okay. And if I take another derivative, right, so this becomes so basically I am just del by del beta of 1 by z times del z by del beta plus 1 by z times del by del beta of del z by del beta. Okay. So, I am just splitting into 2, and this just becomes minus 1 by z squared times del z by del beta times del z by del beta plus 1 by z del square z by del beta squared. Okay. And remember what is okay. So, this just becomes minus 1 by z squared del z by del beta squared plus 1 by z del square z by del beta squared. All right. So, and that is exactly same, right. So, this is exactly same thing. So, 1 by z del squared z by del beta square minus 1 by, and this is exactly the variance of E. Okay. So, all right. So this is what we have. Okay. So basically now we have two results, right. So, we showed that average energy is given by negative of del by del beta of log z, right. So, this is this result, okay. And variance of E is basically is del squared sorry so the second derivative del squared log z by del beta squared, right. And if you look at it closely, I can just rewrite it as minus del by del beta of average energy, right. So, this is nothing but the negative of partial derivative of beta with respect to average energy, right. So, that will exactly give you this. So this now so this can be again rewritten as follows, okay. So, this implies variance of E is equal to so I am just rewriting this term. So, this is minus del by del t of partial derivative of E with now multiplied by partial derivative of temperature with respect to beta, right. So, this is just the chain rule of calculus that I have used, okay. But remember what is beta, okay. So, beta is 1 by kBt. So, this implies my del beta by del t is equal to minus 1 by kBt squared, or I can now take inverse. So, del t by del beta is minus kBt squared, okay. So, now I will just substitute this value here. So, therefore, I can just write. So, okay. So, let's call this 1. So, substituting del t by del beta, the value in 1. So, we can write our variance of E to be as follows. So, this just becomes so there is minus sign here already. So, that cancels out. So, we are left with kB t squared and partial derivative of energy, average energy with respect to temperature, okay. But remember what is this quantity, okay. So, at constant volume, say, so at constant volume del by del t of average energy is basically equivalent to del u by del t at constant volume, right. So, because the average energy in statistical physics is basically the internal energy in thermodynamics, which is u, and if your volume is kept same, the internal energy is exactly equal to the heat supplied, all right, and this is basically just equal to the heat capacity at constant volume, all right. So, this is heat capacity at constant volume, okay. So, therefore, it gives us a very important result that the variance of energy in a canonical ensemble is basically proportional to its heat capacity, okay. So, this is important in a canonical ensemble. Okay. So, therefore, this gives us a very strong understanding of a specific heat, right. So, specific heat is something that we just defined in thermodynamics, right. So, this was the amount of heat required, not specific heat, but heat capacity, but it does not matter. So, the heat capacity is basically the amount of heat required to raise the temperature of a material by some degree Celsius, so unit degree, right. But here now we can actually derive this quantity from the first principle, right, and it is basically just proportional to the variance of energy of that canonical system, which is in contact with the reservoir, which is at constant temperature T, all right. So, therefore, we can now derive such thermodynamic quantities from the very first principle, all right. So, that is one of the successes of statistical physics. Okay, so we will move on to another very important concept which is known as equipartition theorem. Okay, so again let's say we have a huge reservoir. Let's say we have a huge reservoir. Okay, which is again isolated, right? The heat exchange is not allowed. Okay, so this is a reservoir, and we inside it we have a canonical system, canonical ensemble, and say its energy now is a function of some variable x, all right. So this is a subsystem, right, and this is the reservoir at some temperature T, all right, and the energy of this system can be written as say quadratic function of some variable x, all right, and we will take examples of it, all right. So, basically so for a canonical system, in contact, or I can just write a canonical system at temperature T, temperature T, and so its energy is given by the quadratic function of some variable x, okay, it can be anything. So, there is some proportionality constant times x squared, okay, but this quadratic is important, all right. Then we can write its average energy as minus infinity to infinity E times e raised to the power minus beta beta E dx divided by, or I can okay, minus beta E, which is now alpha x squared dx divided by minus infinity to infinity e raised to the power minus beta alpha x squared dx, right. So, this is how we can define its average energy, all right, and this can be written as follows. So, this is so now I can replace E here as well. So, alpha minus infinity to infinity x squared e raised to the power minus beta alpha x squared dx divided by minus infinity to infinity e raised to the power minus beta alpha x squared dx. Okay. And since this is an even integral, so what we can do is we can write both denominator and numerator as following. So, 2 alpha times the limits going from minus infinity to plus infinity. So, they can go from 0 to infinity x squared e raised to the power minus beta alpha x squared dx and divided by 2 times integral 0 to infinity e raised to the power minus beta alpha x squared dx, and clearly the 2 cancels out, and the integral that we eventually have to solve is basically just this, right. So, with the limits now going from 0 to infinity, right. So, let us first do numerator. So, numerator, okay. So, in numerator we already have seen this. So, it is a gamma function which okay. So, for any okay. So, for any general integral of such a form which is 0 to infinity e raised to the power minus beta x squared x and dx. So, this is basically given by 1 by 2b n plus 1 by 2 times gamma of n plus 1 by 2, right. So, all right, and so we already and we know for n equals 2. So, the gamma of 2 plus 1 by 2 is basically square root of pi by 2, all right. And denominator is a standard Gaussian integral, right. So, it is a Gaussian integral, okay. And the value of okay, so the denominator is minus infinity to infinity e raised to the power minus beta alpha x squared dx, right. So, for any Gaussian integral which looks like e raised to the power minus b x squared dx, so the value is square root of pi divided by the quantity which is sitting in front of x squared, okay. So, this is just pi divided by beta alpha and this is half, okay. So, now if we substitute these values there, so if we substitute those back here, so, so we get our average energy to be equal to alpha divided by 2b. So, this becomes alpha by 2b basically 2 plus 1 by 2, right. And remember what is b here, now b is beta times alpha, all right. And this is gamma 2 plus 1 by 2 and whole thing divided by 1 by 2 square root of pi by b, okay. So, here I am using b as a shorthand notation of b times alpha, all right. And if I now substitute this gamma 2 plus 1 by 2 as square root of pi by 2 and you do this simplification, you can easily check that this is equal to 1 by 2 beta, all right. So, that tells me that that if my energy function has a single parameter, single quadratic parameter, all right. So, so my average energy just becomes 1 by 2 beta, and what is beta? This is kBT by 2. And now if I consider, and if I consider a more general case, right. So, for a more general case, so we can imagine energy to be function of energy function to be look like this, right. So, alpha 1 x 1 squared plus alpha 2 x 2 squared plus so on plus alpha f x f squared, all right. And if we now plug that back into this and we evaluate the average energy, so you can very simply see that in this case the average energy will come out to be f by 2 kBT, all right. And where f is known as degree of freedom, okay. And that basically tells you the number of quadratic terms present in the energy function, all right, of any system. And we have actually already seen examples of it, right. So, we saw that for an ideal gas, so for an ideal gas, so E is basically half m Vx squared plus half m Vy squared plus half m Vz squared, all right. And clearly since the energy is just sum of kinetic energies in all coordinates, so its degree of freedom is 3, all right. But we can see that how for more complicated systems the degree of freedom can be different, right. So, basically we can see that if we have a diatomic molecule, so say we have a diatomic molecule, this is one atom, this is another atom and connected together with a bond, right. So, this is the bond and say this is so this is x axis, this is y axis, this is z axis, right. So, there is so for such a system, okay, so I can write its energy. So, for a diatomic system, so energy is given by half m Vx squared plus half m Vy squared plus half m Vz square, where now m is the total mass of this molecule and this is basically this basically means the translational degree of freedom, right. So, this molecule can move in space in 3 dimensions, 3 directions, but on top of that it can also like now rotate, right. So, it can also spin either around this axis or around this axis, right. So, and we are assuming that any rotation along this axis does not really change change anything, because the molecule is symmetric along that axis, right. So, I can write this as Lx squared by 2 Ix plus Ly Ly squared by 2 Iy. So, where Lx, Ly are the angular momenta along x and y axis, and Ix and Iy is the moment of inertia of this molecule. And now you can see that the energy function for such a system has 5 quadratic terms, right. So, this implies the degree of freedom for such a molecule is 5, all right, and so on. Okay. So, for more complicated looking molecules, the degree of freedom can be much higher. Okay. So, and this will imply that average energy will be 5 by 2 kBT. Okay. So, now let us say we have Na number of molecules, right. So, say we have 1 mole of gas. Okay. So, for 1 mole of gas with Avogadro number of molecules. Okay. So, what will be the total energy? So, E total would be the number of molecules times average energy, which is equal to F by 2 Na kBT, right. So, I am just substituting for average energy as F by 2 kBT, and we know Na times Kb is the gas constant. So, this is F by 2 RT, all right. And what will be the heat capacity, right. So, heat capacity at constant volume, that will be del E total by del T, right, at constant volume, and this just becomes Fr by 2. Okay. And we also know for an ideal gas, so Cp is basically Cv plus R, and if I substitute Cv here, so this just becomes F by 2 plus 1 times R, and now we can also calculate the adiabatic index, which is Cp by Cv. So, this is F by 2 plus 1 divided by F by 2. So, this is 1 plus 2 by F. Okay. So, this is the adiabatic index of any gas, assuming that it is an ideal with F degrees of freedom, all right. So, okay. So, now we can basically take okay. So, we can now summarize this thing. So, say we have a gas, it has various modes, right, various basically the number of quadratic terms or modes in which it can store energy. It has F, and it has corresponding average energy, and it has corresponding adiabatic index, all right. So, what we have seen so far is for a monoatomic gas, there are 3 translational modes, right, 3 modes. So, therefore, its degree of freedom is 3, its average energy is 3 by 2 kBT, and its gamma is 5 by 3, right. So, if you just substitute 3 here, so you get 5 by 3. So, for a diatomic gas, okay, so we have 3 translational, so I can just write T for translational, T 3, and we have 2 rotational modes, right. So, therefore, degrees of freedom is 5. So, we have 5 by 2 kBT, and if you substitute 5 here, you have 7 by 5. But this is true only at low temperatures, right. So, something else can happen at high temperature. So, if I increase the temperature, so this molecule can even vibrate like this, right. So, its bonds can do like this, all right, or the other thing that can happen is, so like they can even vibrate like this, right. So, there can be 2 vibrational modes, and for low and for low enough amplitudes or low enough displacements, we can always do Taylor series expansion and assume those modes to be simple harmonic oscillators. So therefore, we will definitely end up with a quadratic term in the leading order, right. So therefore, therefore in this case, so this is at low T basically. So at diatomic gas, at high T, okay, at high T, in that case we will have again 3 translational mode, 2 rotational mode, but we will also have 2 vibrational mode, okay. And you can clearly see here there are 7 degrees of, so 7 degrees of freedom, and we have 7 by 2 kBT, and this becomes 9 by 7 and so on. I now go to carbon dioxide, for example, right. So carbon dioxide has like double bond with oxygen, right. So these are oxygen molecules, and this molecule can like undergo rotations like this or like that. There can be multiple vibrational modes where the oxygen atoms are moving like this, or the carbon atom is moving out of plane and so on. So you can see that the number of degrees of freedom in this case will be much higher. You can even think about even more complex gas, right. So for example, methane. So you have hydrogen, so 3 hydrogen atoms, right. So in this case there will be even more number of degrees of freedom, right. So that is how we can basically so just from the energy function, how many quadratic terms there are, we can determine the degrees of freedom, and we can calculate quantities like average energy as well as adiabatic index for those gases. So in the remaining time, so the next thing that we will do is we will basically try to now basically come back to the ideal gas equation, right. So we have basically now formulated the concepts of statistical physics, and now we want to check whether we can now derive the ideal gas equation from the concepts that we have developed, all right. So let us do that. Okay. So basically what we will start with is again the definition of average energy in canonical ensemble, right. So basically average okay. But now we will take the case not of discrete energy levels, but of continuous energy levels, right. So for continuous energy states, so for continuous energy states, so the partition function, the canonical partition function can be written as follows. So z is 0 to infinity dE times e raised to the power minus beta e and its derivative with respect to e, where d, capital D is density of states, right, density, and we saw that in 3 dimensions. So we saw that in 3 dimensions, and for one particle it scales as e raised to the power half, right. So in 3D for one particle. Okay. And therefore we can write dE for in general for n particles it will scale as e raised to the power n by 2, right. And remember what does so from partition function, right, if you could try to compute the probability, which is e raised to the power minus beta times e, right. So clearly if your e is low, there will be more probability to exist in that energy state, all right. So therefore in canonical ensemble the probability to be in a lower energy state is always maximum, but right. But however, you should understand that since the density of states also increases as a function of E, there are very few states, in fact there are no states at energy 0, all right, and the number of states available for the system increases increases very fastly as a function of energy, right. So, therefore, on average system always sits in an energy which is not 0, but greater than 0, right. So, what I am saying is the average energy which we can now call E average is always some finite number which is greater than 0, right. And what we can now do is we can basically just plug these values in here, and we can calculate our partition function as follows. So, we can just write our partition function as so what we can now do is, so we can see that the density of states time dE, but now computed at near the average energy E bar, that will be just equal to the number of microstates corresponding to energy E bar, right. That means we have a system which has a fixed energy E bar, and that is the number of microstates in that, right. And therefore, we can write our canonical the partition function. So, we can write our partition function as e raised to the power minus beta E bar times omega E bar, all right. So, this is how we can rewrite the partition function. So, now we can take log on both sides. So, then we can write log of z is basically equal to minus beta E average plus log omega of E average, right. And if we divide both sides by minus beta, right. So, this becomes and what is minus beta, that is minus 1 by beta is minus k bt. So, this becomes minus k bt log z is energy, average energy E minus k bt times log of omega E average, okay. And this simply becomes, okay. So, this is basically equal to, now we can now go back to the thermodynamics. So, the average E is basically internal energy minus T times Kb log of omega, right, E average, okay. And what is this quantity? This is basically entropy, right. So, this can be written as, okay. So, therefore, the log of z, so this implies log z is equal to, sorry, this is minus kbt log z, okay. So, this implies minus kbt log z can be written as u minus Ts, which is equal to the Helmholtz potential, right, Helmholtz potential, okay. So, therefore, I can write my partition function, okay. So, if I rewrite this, if I take exponential on both sides, so this just becomes e raised to the power minus beta f, minus beta f, and this is an important result, right. So, this is essentially telling you a simplified form of canonical partition function in terms of the Helmholtz potential, all right. Okay. So, now remember we know that f is u minus Ts, right. So, this implies our f df becomes du minus Tds minus Sdt, and for an ensemble where particle exchange is also allowed, and this basically can be written as Tds minus Pdv minus Tds minus Sdt, right. So, this cancels out. So, we are left with minus Pdv minus Sdt, okay. So, therefore, I can rewrite my pressure as negative of partial derivative of Helmholtz potential with respect to volume at constant temperature, all right. Okay. And now remember what is F. So, from this relation we can write our Helmholtz potential as minus kBT times log of z, right. And if I substitute it here, So, so I can rewrite, okay, and this is what f is. But now what is now see now what we have to do is we have to determine z, all right. So, what is z? So, z is the partition function which by definition is sum over all states, okay. So, minus beta ei, where now this sum is over all the states of all the molecules, right. So, energy states of all gas molecules, okay, because we are working with many particles now, all right. And the partition function we have to sum over all those energy states, and that will be our partition function. But now remember, so in ideal gas the molecules are moving independently, they do not really interact with each other, right. So, therefore, the total energy of an ideal gas is basically sum of kinetic energies of all the individual gas molecules, right. So, but since for ideal gas, so what is E, right. So, E is basically epsilon 1 plus epsilon 2 plus so on up to epsilon n, right. So, this is sum of kinetic energies of all the individual gas molecules. So, therefore, I can write my partition function as follows. So, this is sum over e raised to the power minus beta times epsilon 1 plus epsilon 2 plus so on plus epsilon n, all right. And again this is summed over energy states of all molecule. But since okay, so so now I can also define the average kinetic energy, right. So, average kinetic energy per molecule. So, let me call that as epsilon, that is basically equal to E by n, right, and this is basically epsilon 1 plus epsilon 2 plus so on up to epsilon n divided by n, all right. So, therefore, I can now express my sum of all the kinetic energies in terms of n times average kinetic energy and plug it here, right. So, therefore, I can write my z as again sum over all states, right. So, same thing, e raised to the power minus beta n times epsilon, where now epsilon is the average kinetic energy. And I can now basically simplify this, and this is an important step. So, I can just write it as beta times epsilon raised to the power n, but now this sum will be carried over all the energy states of single gas molecule, right. So, energy states of single gas molecule, all right. So, and now basically we can now do that sum and write it in the form of integral, and this, if you remember, this was 1 by h cube. The first we will do the space integral, right, in the real space, and then 0 to infinity d cube of p e raised to the power minus beta p squared by 2m, right. So, this is the kinetic energy or average kinetic energy of single molecule. So, basically we are summing up all these number of microstates in the phase space, all right, and this whole thing raised to the power n. So, whole thing raised to the power n, okay, and the integral over our space will just give you volume divided by h cube, and this goes from 0 to infinity dpx e raised to the power minus px squared by 2m, 0 to infinity dpy e raised to the power minus py squared by 2m, and similarly the third term 0 to infinity e raised dpz minus pz square by 2m, and this entire thing raised to the power n, Okay. And again we can use the Gaussian integral, all right, and this becomes V by h cube times, so Gaussian integral is square root of pi divided by the term which comes in front of px, which is 1 by 2m. So there should be beta here, beta everywhere. Okay. So there is beta, so that is beta by 2m. Okay. So this becomes V by h cube times pi divided by beta by 2m, and whole this thing raised to the power 3 by 2 and whole thing raised to the power n. Okay. And this is, say, our result number 1, all right, equation number 1. But now remember, so f is minus kbt log z, right, and I can, so this is z, right, so I can take log of this quantity, so this is minus kbt. Okay, n comes in front after taking log, so I can write it as follows: log v, so I am separating the v term, plus log of everything else, right. So log of log of 1 by h cube times pi by beta by 2m raised to the power 3 by 2, right. And since the pressure is given by negative of partial derivative of Helmholtz potential with respect to volume at fixed temperature, right, at fixed temperature, I can just write it as follows. So this becomes P equals, so if I do that, this can be written as kBT n kBT divided by V, right. And if you check that, this will exactly give you the ideal gas equation, PV equals n kBT for n number of gas molecules. Okay. So this is the ideal gas equation. Okay. So this way we can see that we can actually derive the ideal gas equation from the concepts of statistical physics, and so there is like this internal consistency in the theory that we have developed. All right. So I will see you in the next class. Thank you.